Now we're going to use material that we've dealt with already. I'm looking here. Will you make a note, please, of every past exam question I dip into so you can revisit it in your own time? All you need to note for the moment now is 2006, question 11a. 2006, question 11a. And I'm dealing with now the material I've just done in the last unit to see how you're dealing with this. I can't do all that question at the moment, which is a point I'm trying to make to you. That until we get this section done completely and the next section on stoichiometry, there will be aspects of your chemistry struggling. So please be patient and you'll do fine. I'm going to see how far we can go with this. The question asks you 11a, what is an ideal gas? And that's a straightforward answer, I hope. Okay, this is a gas which obeys all the assumptions of the kinetic theory under all conditions of temperature and pressure. Now, I don't know that law or I don't know that definition. I simply am articulating an idea to you. Are you doing the same? It's very important because that's what I want you to do. Okay, if you do, you'll be fine. Next, part 2. Give one reason why a real gas like carbon dioxide deviates from ideal behavior. There's carbon dioxide. Now, I don't want to overemphasize this at the moment, but I'm working on the premise that you have chemical bonding done and that you're okay with that. The intermolecular bonds, here we go again, will come in here. Give one reason. Now, there could be any reason. You could say, for example, the constant random motion one isn't the best. I recommended number 2 and 3 to you. Okay, and so they're the two you should probably be looking at. There are no attractive forces between the particles. Do you know something about the structure of that molecule? Carbon in the middle, 2 bonds here and 2 bonds there. Okay, carbon has a valency of 4 and oxygen has a valency of 2. Oxygen has 2 bonds, carbon has 4 bonds. Now, that is a linear molecule and it is non-polar. Non-polar, P-O-L-A-R, right? If you were going that would be delta minus and that would be delta plus. That's delta minus and that's delta plus. So the center of the pluses is there. All the pluses are in there and the center of the minuses is there as well. So even though there's a polar bond there, that's a non-polar molecule. And they're probably teasing you with that particular example to see how you'll cope with it, okay? But in fact, the reality is that's a non-polar bond. So it has van der Waals forces. What's your spelling there, please? Van der, W-A-A-L-S, van der Waals forces. Okay, so there are bonds between these molecules that you wouldn't have for an ideal gas. So carbon dioxide varies from that. Now be careful there, there's only 3 marks for it. They're not looking for an essay. Give one reason why a real gas like carbon dioxide deviates from ideal behavior. You could have mentioned, for example, carbon dioxide is a fairly big molecule and therefore it occupies some space. There's another reason. It's a second example, okay? But the first one would be fine. That would be a very good example because, of course, you have chemistry to support it. But if you were to say, in an ideal gas, the particles occupy no space. Carbon dioxide is a large molecule. It occupies some space. And that would be fine, okay? And the constant random motion one I've mentioned to you already, when the carbon dioxide molecules would collide, they would become stationary for a moment. Therefore, they're not constantly moving. Any one of them would get you those 3 marks there. Assuming ideal behavior, how many moles of carbon dioxide are present in, and they've given you data here on this now that you have to work with. Now, as I advised you in the last unit, take down the data from the question on your manuscript in the exam, okay? So you're talking here about carbon dioxide. I'm just making a note of the fact it's carbon dioxide. It's irrelevant other than that. There's 72, V equals 720 centimeters cubed, right there, okay? And the gas at temperature of 10 degrees Celsius, 10 degrees Celsius, and a pressure, and it gave you the pressure of 1 by 10 to the power of 5 pascals. Now always check you have it down right, that's correct. And it asks you to give your answer to one significant figure. Now, all I'm mentioning to you in this is that you need to do that every time. I'm more interested now in your method than your solution. Because if you have a good method, you tend to get these calculations right all the time. Okay, there's no point doing it well now and then not doing it again. You must always do that, okay? Now, you know, of course, anytime you're given the volume of a gas at a stated temperature and pressure, you have a formula with which you can calculate the number of moles present, and there you go. PV equals nRT. Okay, and therefore N equals PV over RT. Very good. Now you can't substitute them in there. Do you know what I'm going to tell you next? Yes, you must convert them to metric. Okay, so you should do that on your manuscript. That would be 720 by 10 to the power of minus 6. Okay, that would be 273 and add 10 to it, 283 Kelvin. And this, of course, is already in pascals. You've nothing to change. Metric, metric, and metric. Pop those three numbers in there. And sorry, I should be telling you about R, of course. R will be given to you, 8.31, and it's metric units. Okay, always metric. Don't worry about it, and don't worry about the units. If you wanted the units, by the way, you could solve for R in that, and you get it in terms of the others, and that would be very good. And if you did that, you'd have got an answer of 0.03 moles. N equals 0.03 moles. And of course, it's carbon dioxide, I'm reminding you. There's your answer. Always give a number, always give a unit, and always tag your work in chemistry, because there are so many different chemicals that you deal with in the course of a chemical question that you'll get confused. Okay, very important. Now, I'm more interested in layout here than any solution. You'll do that with a calculator, of course. Now, that will be written next. Put in all your numbers, evaluate the top line and write it out, evaluate the bottom line and write it out, and then evaluate the quotient, and you're going to get your value for N. Now, please, you'd show all that work, but that's very important to me. Now, most candidates do not do that. Please change, okay? Please adapt, so you're always getting things right. You'll do well if you do. Now, I can't do much more of this for the moment. It asks you there, okay? It asks you there, how many molecules of carbon dioxide are present in this quantity of carbon dioxide, okay? They've asked you initially to get the number of moles. I need to deal with the mole before I can deal with that. Will you take my word for it? We've now got the mole, and it's very easy to go to particles or whatever from there. That's a separate unit that I'm going to be doing with you very shortly, all right? But I'm just showing you that. And then there's a further piece, which is a piece of stoichiometry. Now, none of that is difficult, I want to say to you, but you must have all the units done to handle that well. Now, please be very, very careful that you're not losing any of those marks, because they're easy to control, and you get your marks very, very easily there. I'm going to show you a second one. I'm looking at 2009, and we're looking at question 10a. 2009, question 10a. Let me do that one for you. 2009, question 10a. 2009, question 10a. These are all worth 25 marks, remember, and look how they're dealing with it there again now. State Avogadro's law. Can you do that? There are 4 laws on your course. Are you okay with all 4 of them? Avogadro's law states that equal volumes of different gases under the same conditions of temperature and pressure contain the same number of molecules, okay, the same number of particles, and there's 7 marks for that. Give 2 assumptions of the kinetic theory of gases. Here we go again. Okay, please try and work from the top down, I've told you. The next part, give 2 reasons why real gases deviate from ideal behavior. Now, will you be careful, please? Will you be careful that you pick the right assumptions, okay? The first 3 are there. Gas particles are in constant random motion, okay? Number 2, the gas particles have no attractive forces between them. And number 3, the gas particles occupy no space. Very important that you are using them every time. Give 2 reasons why real gases deviate from ideal behavior. They didn't specify any gas, and that's good for you. So you simply say things like, now I would say always, I would go for number 2 and number 3 every time, because you have a lot of chemistry to support them. Number 2 in particular, there are attractive forces between real gas particles. And because you're doing chemistry, you should now be able to tell me what they are. And that's okay, isn't it? There's no problem there. What are they? They are simply van der Waals forces, dipole-dipole forces, or hydrogen bonding, depending on the gas molecule involved. I'm reminding you briefly again, if the gas particles happen to be polar, it will either be hydrogen bonding or dipole-dipole, and if they're non-polar, it will be van der Waals. You didn't need to say that now, but I'm only mentioning that to you. That would be one reason, okay? And second, then, 2 reasons why real gases deviate from ideal behavior. All real gases, particles, occupy some space. irrespective of how small they might be, they occupy some space. An ideal gas says they occupy no space. So that would be the second one. And if you needed a third one, I would go back to number one and say gas particles are not in, real gases are not in constant random motion, because when they collide with the walls of the container or with other particles, they become stationary for a moment in time before moving off again. So they're not constantly moving, and that's rather important. I've advised you stay away from the two later assumptions. I hope you're taking heed of that. And the last bit, once again now, I would rather wait until I've done the mole with you, which I'm about to do right now. Okay, and that's very important that you have a sense of that. I'm about to get into the mole with you, and then we can complete those questions as you would do that. But I hope that's giving you some sense of the relevance of what you're being asked. Okay, and so at last we've got to the mole. Now take a look at our plan again, because it's very important. You must go back and revise relative atomic mass and relative molecular mass now if you're to deal with the mole down here. And you'll have great difficulty with the mole if you haven't the gas section done. Okay, and we've gone through all that in the last few modules now. Okay, you've just done kinetic theory of gases and an ideal gas. And we got the ideal gas equation out of that. This particular equation, PV equals nRT, has two possible names. It could be called the equation of state for an ideal gas, or it could simply be called the ideal gas equation. Now, if they choose to use either of those names, you'll recognize it because the word ideal will be in it. And that's the formula then, PV equals nRT. I'll be back to do calculations on that in due course. I just need to do the mole with you firstly, and we're about to do that now, the mole. Now, you'll be asked what is the mole, or define the mole. And it is a quantity used by the chemist. Surprise, surprise, it's a metric quantity. Even we don't tend to make a big deal of that. It's a metric quantity. And it's a fairly large quantity. And most people do not appreciate how large it is. This is the amount of a substance. And I'm using the word substance here, and I generally don't recommend it in chemistry. It's usually used by bluffers when they don't know what they're talking about. You see, substance here covers everything, if you know what I mean, and that's what I'm trying to do here. It's the amount of a substance which contains an exact number of particles, and that number of particles is known as Avogadro's number, or Avogadro's constant. 6, okay, I just leave it at 6 by 10 to the power of 23. It's available to you in the formula tables. You go there to page, the appropriate page 46, 47, and you'll find it there for yourself. It is also likely to be printed on the front of a chemistry paper. Okay, but it's something, it's the bread and butter for us in chemistry that you know that number, Avogadro's constant. What is Avogadro's constant? Oh, that's the number of particles present in a mole. What is a mole? A mole is the quantity which has that many particles. You see there's a link in them there, like that, and that's how it. So what does a mole look like then? I think we'd have to have some sense of that. I don't think we know a lot about it. I'll have to come back in it shortly to deal with that, but it would be a big lump of carbon, which is very light, which has a mass of 12 grams. Or it would be a huge, long ribbon of magnesium, which is very low in density as well, and to get 24 grams of it. Or there'd be two very big flasks of gas, if you were talking about a mole. Before we can deal with the mole, I suppose, we need to know certain facts about it, and I'm going to put them on the screen for you now, and I'd ask you to heed, please. Now, there's a copy of this to follow. You will get a copy of this particular page because there's questions to go with it that we have to deal with. There are certain facts about the mole that every chemistry student has to know, and you need to be very aware of this now. 1 mole of a substance contains that many particles. Now, I'd always want you to say, when you say particles there, the particles could be atoms, if you were talking about something like helium gas, it could be atoms because they don't join with anything. Or it could be molecules, if you were talking about a mole of water. Or it could be ions, if you were talking about copper sulfate. CuSO4 is made up of Cu2 plus ions and SO4 double minus ions. So there would be 6 by 10 to the power of 23 copper ions in a mole of copper sulfate. Are you okay with that idea? That the word particles there could mean atoms, it could mean molecules, or it could mean ions, depending on what substance you're speaking of. So just be aware of that. And I ask you again now, please, tag all your work. Please always tell the examiner the substance that you are referring to. It's good for you too, because you won't make silly mistakes. Okay, so every time you do that, please tag your work and you won't go wrong. So a mole would contain that many particles. Next, a mole has a very specific mass, and here we go. You couldn't understand the mole without having masses and gases done already. And we have that done in the first unit now. What is the relative atomic mass? You remember that now? This is an average mass, taking the isotopes into account. Do you remember this? Taking their abundance into account and expressing them on a scale where carbon 12 is 12, or words to that effect now. You need to adopt your own definition there. Which one are you going to use? This is the average mass of an atom of an element compared with 1/12 of the mass of the carbon 12 isotope. You have a formal definition for that now. Be very careful. And remember, will you, all the ARs you will need will be printed on the front cover of your Leaving Cert paper. And they're also available printed in the formula tables that are presented to you in the Leaving Cert. Okay, you will find them, of course, right, in this, but you will be given the rounded off values for calculation purposes here, right? And they'll write things like carbon equals 12, hydrogen equals 1, copper equals 63.5, I think. I have to look it up, okay? The idea that you should have to know these is silly, but they'd be given to you. Are you okay? So the AR will be given. So 1 mole of carbon has a mass of 12 grams. So if you've got a big lump of carbon, okay, 12 grams, that would be a mole of carbon. Okay, and hydrogen, well, hydrogen doesn't exist on its own, but I am making the point to you that it would be 2 grams because it would be H2 to be the gas. And copper, of course, if you had 1 mole of copper, you'd have 63.5 grams of the copper. 63.5 grams of copper would be a mole of copper. That'd be a lot of copper, by the way. Okay, copper is, you know, you'd have quite a bit of copper in 63.5 grams. And that's exactly what you're after, right? In that. Now, that's the relative atomic mass, and we're dealing with atoms here. Now, we need to be careful. This fellow here, you see, is a molecule. Okay, that would exist as H2. So obviously then, you'd be talking about 2 grams. 2 grams of hydrogen gas. Okay, as it's a molecule. If it was water, H2O molecule, then it would be 2 ones, 2 multiplied by 1 plus 16, and that would be 18 grams. So 18 grams of water would be 1 mole, right? And, you know, you could get silly about this. There is benzene, C6H6. You'd have 6 12s are 72, 6 by 12, and you'd have 6 by 1. Are you okay? 6 12s are 72, 72 and 6 is 78 grams. 78 grams. All right, and that's very important that you have a sense of that. They're molecules, okay, so they're MRs, relative molecular mass. What's the relative molecular mass? This is the mass of a molecule of a substance, isn't it? Molecule of a compound or element, right? Compared with 1/12 of the mass of the carbon 12 isotope. And of course, I didn't put in the word average there. It's the average mass, okay? And they're the 2. So if you happen to know the name of the stuff you're talking about, you happen to know the mass, or you can very easily calculate the mass of a mole of that substance. And I think that's something you should work with, because I think more than anything else, that's an important way of dealing with the material. If you do, you'll be grand. Okay, so I've done that for you. I think you're okay for the moment with that. I'm going to move on. The third aspect of the mole you can see there has to do with gases. If you happen to be dealing with a gas, then 1 mole of that gas has a volume of 22.4 litres at STP, or 24 litres at RTP. Now, will you be very careful? Unless they say STP, they don't mean STP. They do not have to say RTP, room temperature and pressure. If I tell you I have a flask there and there's a gas in it, which I'll be dealing with later, if I told you I have a flask with a gas in it, well then, would you take it, please, that it's in the room, and therefore it is RTP, and therefore that's the magic number for you. Okay, I'd expect you to be aware of that. They have to say STP to you. If they don't say STP, it is RTP. Now, please, just be aware of that. Now, have you some sense of the size of that, I wonder? The size of a mole of gas. Let me show you. There's the size of a mole of gas. Okay, there's 22.4 litres of gas there. Okay, that's the size of it. Now, normally when you'd have a gas, you'd have a little test tube. you'd have a little test tube and you might have your gas inside it and a stopper on it, okay? And that'd be a tiny fraction of that. So when someone says to you to calculate, they would say something to you like, calculate the number of moles you have. If you found yourself getting an answer of 654 moles of gas, right? And we'll take the gas for the moment to be, let me stay with the carbon dioxide. Now, will you take it? You've probably made a serious calculating error there. If you had 654 of them, with all due respect, we wouldn't fit in the room, okay? So you've made an obvious mistake. It's much more likely when you're doing calculations relating to lab work that you have something like 0.0125 moles would be much more likely. What am I suggesting to you? I'm suggesting that the mole is a very big quantity, and most of the time when you're asked, how many moles do you have? You end up with something like that. That's a good test for regular situations now. That's not to say they wouldn't describe a catastrophe to you and talk about an oil tanker, okay? And it's carrying a particular tanker of gas, and there was an incident and the gas escaped. And they ask you how many moles were lost. Well, then it might be that. But remember, will you, the mole is a big quantity, and I tell you that for particular reasons to do with calculations now, because we're going to get into them very quickly. So there are the three facts you must know about the mole. Do you think you have them now? And do you think you're aware of them? You know how many particles are in a mole? Particles could be molecules, could be atoms, or could be ions. You know the mass of the number of moles. If you know the substance, you nearly always do. They'll name the substance for you, ammonia gas maybe carbon dioxide, maybe a metal, a named metal or whatever, okay? So you generally, and if you do, of course, then you know what the mass of a mole would be. And lastly, if they're talking strictly about gases, then you can work out the volume of that gas in a mole or the number of moles in a certain volume of gas, which is what I'd like you to think. Right, that should be working with that now. Are you all okay with that? Do you think you have that? Because I'm going to look now at how we would do calculations on this and how we go about them, all right? We don't need these questions anymore now. I wasn't able to finish them until I had the mole done, and I'll come back later and have a look at them, okay? But we do need to look at it like that. Now, okay, so you have that now, and I should be able to say a few things to you now in relation to this. I've mentioned Avogadro's constant to you now as 6.02 by 10 to the power of 23. And before I do anything else, let me just put this up here because I need to make sure that you're getting this right, okay? There's your mole unit there. I'm suggesting to you now 1 mole each of these, all right? It has to be STP if it's 22.4. If they don't mention STP, it's 24. That's called Avogadro's constant, okay? That's its fuller value. The Avogadro constant is the number of carbon atoms present in 12 grams of the carbon-12 isotope. 12 grams of the carbon-12 isotope is 1 mole, and 1 mole would have that many particles. So that's fine. There's no issue with that. I hope you're all right. And that's some kind of an attempt to give you some idea of magnitude or size of a mole. Now, I've done this with you already. I've already said to you that that's the size of a mole. It's very big. It's very big, and you normally wouldn't be using that quantity at all, but it's important to have it. All right, good. Now, next, I'm going to do some calculations on the mole, and we better have some idea as to how we would handle these. Now, I want you to change, if you're not already doing it by this method. I'd like to think you might adapt, because I think I can give you some tips on how you'll eliminate error. Now, you'll all get a copy of this in due course, but I'd want you to, I prefer these are left blank as challenges coming up to an exam, where you can try one again to see how you're doing, okay? How many atoms are there in 1.12 litres of hydrogen sulfide at STP? Okay, now, so what have they done? They're looking for the number of atoms, and they've given you a volume. So wait for it. They've given you a volume, and they want particles. Now, do you realize if you want to go from there to there, you must convert that to moles and then convert that to particles every time. Now, that's what you do, and as a practice, you should do it all the time. I'm going to do that with you now. I don't necessarily going to do this now. I'll give you the answers, I'll give you the method, and I'll let you try them yourselves, okay? But that's very important. 1.12 litres of hydrogen sulfide. I'm writing it down here for you now. 1.12 litres hydrogen sulfide, okay? H2S. It's a smelly gas. Okay, it's a dangerous gas if you inhale it. It's a smelly gas. Would you be expected to know that? I don't think so. I think that would be part of a fuller question, and H2S would have turned up somewhere else in the question. I'm regularly telling classes that you're good at chemistry when you can read the chemistry paper. And that sounds very smart now, but what I mean by that is not just read the words, but read the chemistry. And there's where I want you to be, right? That would have been available somewhere else on the paper, all right? And so how many atoms are there in that many litres of hydrogen sulfide? Okay, so here we go. I have litres. If I want to convert that to moles, it's at STP. I must divide that by 1.12 divided by 1.12 divided by 22.4 is going to give me moles of H2S. Now, I'm not going to do any calculations here, which you simply bung them through a calculator and you have your result. You'll find invariably it will give you a very small value, and that's most important that you would do that, okay? If you do, it'll be fine. So that's moles for you. I've gone from there to there. Now, you divide to go into moles. Why would that be? I've just told you a moment ago that the mole is very big. So when you convert something to moles, the numerical value goes way down, okay? So there's a very small number of moles there, and you have to be alert to that, right? More than if you are, you won't have any issues with it, but I just like to think that you'd handle that correctly, okay? So that's moles. Now that you've got moles, just run that through the calculator, and you're going to do fine with that. Are you okay with that? 0.05? Am I right? 0.05 moles. Now, I don't really want you to be speculating on this. I'm not into numbers, I'm saying to you now. Like most people blame this and saying, well, you know, I made a mistake with the maths. This has nothing to do with maths. It's about good method. And if you've good method, you'll do very well. And I'd like to think you were doing very well. 0.05 moles of H2S. Okay? How do I get from moles then to particles? Easy. 0.05 multiplied by 6 by 10 to the power of 23. And you must label that now. Are you ready? You must label that. And that is equal to, are you okay with this? That's equal to, in this case, molecules. Molecules of H2S. Now, I'm big into this, and I'm asking you now to please adapt. It's very important that there's a number, that there's a unit, and that there's a tag throughout chemistry. That you're always talking the talk. You never make mistakes if you do that. And I strongly urge you to do that now, please. That's what they want from you. 0.05 multiplied by this is going to give a number of molecules, okay? And you're going to get there, are you? A half, that's going to give you 3.0 by 10 to the power of 22, he says, chancing his arm, molecules of H2S. Now, please, don't be cavalier with numbers. I'm only meddling with them here, okay? I'm just saying that to you, okay? Half of that would have been 3, okay? And divide by 10 then, and you have 2. Now, please, use a calculator every time, and please repeat all the writing. That's molecules. Now, there is no abbreviation for molecules. The abbreviation for the mole, by the way, M-O-L-E, is M-O-L. Isn't that fascinating? M-O-L-E is abbreviated to M-O-L. Now, please, notation in chemistry is very important. And people start writing things like moles. Moles. My writing isn't great either. Moles for molecules. That's wrong. That's moles. Don't do that, okay? Write it out in full every time, and you won't make mistakes. So I have molecules of that. Is that what they asked me? Is that what they've asked me? How many atoms are there? No, they didn't. But I had to get molecules because that's a molecular substance. Okay, finally you have to make a statement, and I like when people put some words into their answers to kind of clarify what to do. Each molecule, one molecule, has 3 atoms. This is an eye test, guys, okay? 2 and 1, 3. So you must multiply that number by 3. And you'll get 9.0 by 10 to the power of 22 atoms. And for once, you don't have a tag, because it could be hydrogen atoms or sulfur atoms, you follow? They could have asked you in that question, how many hydrogen atoms are in that? So you'd still have to get to here. And then you'd say each molecule has 2 hydrogen atoms, so you'd multiply by 2. Now, please, what's good about that? The number of lines. Many of you guys would do that in 2 lines now. You'd be skipping pieces there. Don't do that, please. You must get all the marks in these things. You've total control over that. And I'm just reminding what we did now. Someone gave you a volume of a gas, and they wanted to know how many particles were in it. You have to convert the volume to moles by dividing always. You go into moles by dividing, and you come out of moles by multiplying. And that's very important, that you're aware of that and that you have a sense of that. If you have, you do very well. Now, do you think you're okay in dealing with that one? Now, that's just one question in relation to that. Now, that little collage should be around all the time when you're working. I went from there to there and there to there. You could go for any one of these to any other one of them, and that's vitally important that you get that right. Now, I'm going to do a second one with you, and I will break it at that then for the moment. This is the second one that I'm going to do now. Are you okay? This one here. Now, you need, in each case, when you're doing these, you need to kind of lay out everything, write down every fact they give you, every detail, and make sure that you're dealing with it correctly. Okay, as follows now. This one, a lamp filled with neon gas contains 7.5 by 10 to the power of 21 atoms. What is the capacity of the lamp? Capacity is volume. So they have given you, they have given you particles and they want to know the volume. Okay, and we're going to work with that now quite easy. Okay, they are speaking a lamp filled with neon gas. So you have 7.5 multiplied by 10 to the power of 21, and it is neon atoms. Okay, it is written there as atoms of neon, and neon is an inert gas. It doesn't join with anything, it doesn't bond with anything, so that's correct. A gas filled with neon gas contains that many atoms. What is the capacity? You must now go to moles. That's 7.5 multiplied by 10 to the power of 21 divided by 6 by 10 to the power of 23, and that's going to give you moles of neon. Now please, a number, a unit and a tag every time. Okay, very easy now, you'll have no problem with that. And the number of moles is going to be quite small, I'm sure you realize that. Okay, it's going to be quite small, right? Chancing my arm, 0.025 he says. No, I'll leave it go at that. Okay, that you're fine. Okay, that's it's 125 maybe, not 125, 125. Okay, like that. Now please don't worry about that. You must go and do that yourself. You must run it through a calculator and you'll get that. Now you have moles. You've gone from particles to moles. Now you must go. It asked you for the capacity of the lamp. Did they mention STP? No. Where are you likely to find a lamp? The answer is in the room. Okay, so it would be a room temperature and pressure. So you take that value there, moles, and you multiply it by 24.0 litres of neon. And there you go, right? And there you go. And your answer would be, in this instance, it comes out as, where have I got my numbers? That should have come out to be, the volume should have come out to be 0. When you get that, it'll be 0.03. 0.3 litres. Is what I have there. 0.3 is right. 0.3 litres of neon. Now guys, again, a number, a unit and a tag. Okay, number, a unit and a tag. Now don't worry about that, I'm only making the point that you'll just have to realise. Take your number, when you get it from there, write it down. Put the number here, multiply by that, and you get this. Stop skipping lines. The error rate in chemistry is frighteningly high. For good students now I'm talking about. Okay, the idea at times I'm leaving with the impression people are careless with their maths. No. These are people who have a good standard in chemistry but are screwing up the results. Now please be careful, that's very important, okay? I have a certain contempt for numbers, it's a waste of my time. But you need to be very careful with them, okay? I'd rather be spending time working on chemistry with you, but you must make sure you don't make mistakes there. 0.3 litres of neon is what you've got there, okay? Some of you might like to write that as 300 centimetres cubed of neon. By the way, they're both correct. They're both correct. Okay, that's what you got there, because ultimately you understand you're working with this. You're working with this. You follow? You're working with litres, so it had to be litres initially before you got that. That would get full marks. Sometimes when it's a small number, you would change the units. That's a matter for yourself. I'm quite okay with that. Now, I need you to kind of digest that now first and get a sense of that, and then we'll follow that up now with further applications of that and further exam questions. Okay, so we'll break on that for a moment.